Two colossal cities of stars are on a billion-year collision course. This is the hidden reality of galactic collisions, the immense events that forge and sculpt the universe. We often see space as serene and peaceful, but the physics behind these encounters reveals a cosmos of breathtaking violence and dynamism. Gravity and the ghostly hand of dark matter choreograph a dance that annihilates old galaxies and births entirely new ones. You will gain a complete understanding of the cosmic forces that literally built the world around you, revealing how the atoms in your body were forged inside stars scattered by these ancient mergers. How can a collision in almost empty space completely reshape a galaxy? What unseen force guides the entire chaotic process? This journey into galactic chaos will forever change how you see the quiet night sky. What hidden story do you think the stars are waiting to tell? Galaxies are the grand cities of the cosmos, each one a vast island of stars, gas, and dust. But they are not static sculptures, they are dynamic structures held in a delicate cosmic balance. On one side, you have the relentless inward pull of gravity, constantly trying to draw everything together. Pushing against this is the orbital motion of billions of stars, all whirling around a common center, creating an outward force that keeps the galaxy from collapsing in on itself. This balancing act defines their shape and their destiny. We see this in our own home, the magnificent spiral of the Milky Way, and in our colossal neighbor, the Andromeda galaxy. These two spirals are already falling towards each other, locked in a gravitational embrace that will, over billions of years, see them merge into a single, new entity, likely a vast, featureless elliptical galaxy. This is not a rare fate. In the early, denser universe, such collisions were the rule, not the exception. Astrophysicists like Dr. Priyamvada Natarajan use powerful supercomputers to simulate these ancient encounters, revealing they are a fundamental engine of cosmic evolution, responsible for the incredible diversity of galaxies we see today. The type of galaxy dramatically shapes the outcome of a collision. A structured spiral with its elegant arms and rotating disk is far more fragile than a dense, football-shaped elliptical galaxy. When they interact, their very architectures predispose them to different futures. Grasping the scale of these events is a challenge in itself. We are talking about processes that unfold over hundreds of millions of years, a timeline that defies human experience. Yet, thanks to the deep field images from telescopes like Hubble and James Webb, we have a unique power. We can look out into the cosmos and see snapshots of this entire billion-year story, from initial approach to final merger, all happening at once in different corners of the sky. This brings us to a profound paradox. A galaxy is mostly empty space. The average distance between stars is so immense that when two galaxies collide, their stars almost never physically strike one another. It is a ghostly intersection. So how does this near miss in the void lead to the complete and total transformation of an entire star system? The answer lies not in the stars themselves, but in the invisible forces that bind them. The true power behind a galactic collision is invisible. We see the brilliant spiral arms and glittering star clouds, but these are merely the surface features of something far deeper. Each galaxy is embedded within a vast, massive halo of dark matter, an unseen ocean that holds the entire structure together. This mysterious substance, which does not emit or absorb light, makes up the overwhelming majority of a galaxy's total mass. It is the hidden architecture, the true skeleton of the cosmos. When two galaxies begin their long approach, it is these immense dark matter halos that make first contact, their gravitational fields reaching out and intertwining long before the stars themselves ever draw near. This invisible hand guides the entire dance. Think of it as a cosmic glue, a gravitational net that pulls the visible stars and gas into a new, combined system. How do we know this unseen ocean is really there? The evidence comes from watching how light itself bends. When two of these dark matter halos interact, their colossal mass acts as a lens, warping the fabric of space and distorting the light from galaxies far in the background. Observatories like the JWST and Rubin Observatory are built to detect these subtle cosmic mirages, providing the most compelling proof that we are surrounded by an invisible framework of mass. The behavior of dark matter is profoundly strange because it does not experience the electromagnetic forces that make normal matter interact. These halos rarely collide or slow down. Instead, they can pass through one another almost like ghosts, yet their gravity is very real. This creates a complex and violent gravitational tug of war. As the dark matter halos swing past each other, their shifting gravitational pull violently stirs the gas and stars within the visible galaxies. Sometimes, the smaller galaxy loses this cosmic battle, its own dark matter stripped away by the larger halo's gravity. This leaves behind ghostly tidal streams of the elusive material, faint rivers of mass that astronomers can only map through their subtle gravitational influence on everything else. Picture dark matter as the powerful, deep ocean current moving beneath the calm surface of stars. You only see the waves on top, but it is the relentless current below that determines where the entire system is ultimately going. This invisible framework does not just set the stage for the drama to come, it writes the script for the stellar chaos that follows. Gravity may be the weakest force in the universe, but it is the conductor of this grand symphony, orchestrating every movement from the first faint pull to the final, merged form. Over immense distances, its quiet whisper begins to bend the paths of entire galaxies, transforming what should be a straight trajectory into a slow, cosmic curve. The two galaxies do not crash head-on. Instead, they swing past each other in a series of graceful yet destructive close encounters. With each pass, they exchange immense amounts of energy and angular momentum, a celestial transaction that fundamentally warps their structures. This is not a simple collision like two billiard balls. It is a chaotic gravitational dance involving billions of individual bodies, a problem so complex that even our most powerful supercomputers can only simulate its broadest strokes. The work of Nobel laureate Kip Thorne and others shows us that every single star, every cloud of gas, and every particle of dark matter exerts a tiny gravitational pull on every other. It is this collective, swirling interplay that dictates the final outcome. The most dramatic effects come from tidal forces. This is the difference in gravity's pull from one side of a galaxy to the other. Imagine holding a handful of dust and ice. As you swing it around, the stronger pull on the side closer to your hand stretches the material out into a long stream. This is exactly what happens to a galaxy. Tidal forces can pull a majestic spiral galaxy apart like cosmic taffy, drawing out immense, shimmering rivers of stars and gas that stretch for hundreds of thousands of light years into the void. We see these spectacular tidal tails in famous colliding galaxies like the antennae, where two spirals have been woven together by gravity into a form that resembles an insect's delicate antennae. But the chaos is not just destructive. As the galaxies interact, their gravitational dance also acts like a cosmic funnel, channeling enormous reservoirs of gas and dust inward toward their very cores. This compression is the key that unlocks the next and most brilliant phase of the collision. This gravitational choreography, for all its beautiful chaos, is merely setting the stage for the true stellar fireworks to come. This compression of gas is where the galactic collision ignites its true fireworks. When galaxies collide, the immense compression of interstellar gas clouds triggers an explosive era of star birth known as a starburst. In these events, the rate of star formation can skyrocket to hundreds or even thousands of times the normal rate we see in a calm galaxy like our Milky Way. These stellar nurseries are often concentrated in the central regions or along the chaotic collision fronts, lighting up the merging galaxies with the brilliant blue light of massive, young, hot stars. These are the giants of the stellar world, burning through their fuel at a ferocious pace and destined to die young in spectacular supernova explosions. We have a perfect cosmic laboratory just next door in the Whirlpool Galaxy and its smaller companion. Hubble Space Telescope observations have resolved individual star-forming regions there, revealing clusters containing thousands of newborn stars packed into areas just a few light-years across. Imagine the entire space between our Sun and its nearest stellar neighbor filled not with emptiness, but with a glittering, dense metropolis of brilliant new suns. The physics behind this incredible burst of creation is rooted in powerful shock waves. As giant molecular clouds, the birthplaces of stars, are slammed together by the galactic collision, their internal pressure increases dramatically. This overwhelming pressure surge defeats the magnetic fields and turbulent motions that normally keep such clouds stable and prevent their collapse. With that support gone, gravity wins, and the clouds begin to implode, initiating a chain reaction of gravitational collapse that forges countless new stars all at once. Yet this period of intense star formation is a cosmic flash in the pan. It is relatively short-lived, perhaps lasting only a few tens of millions of years. The very same supernova and fierce stellar winds from the most massive new stars will eventually blow away the remaining gas, like a cosmic hurricane clearing out the stellar nursery and quenching further formation. This celestial fireworks display is a temporary but brilliant phase, a burst of creative destruction that seeds the future galaxy with new stellar populations for billions of years to come. And within this maelstrom of newborn stars, the most extreme and enigmatic objects in the universe can be forged. Lurking at the heart of nearly every large galaxy, including our own Milky Way, is a sleeping monster, a supermassive black hole. These cosmic giants contain the mass of millions or even billions of suns, yet for most of their existence they are quiet and dark, starved of the fuel they need to awaken. A galactic collision changes everything. The same chaotic dance that triggers starbursts acts as a perfect delivery service, funneling unimaginable amounts of gas and dust directly toward the galactic center. This is a feast for the dormant beast. As this material falls inward, it does not plunge directly into the abyss. Instead, it spirals into a frantic, whirling disk of superheated matter, an accretion disk that glows with the heat of a billion stars. The black hole ignites, transforming from a silent ghost into an active galactic nucleus, or quasar, a beacon so brilliant it can outshine the combined light of every star in its host galaxy. The Chandra X-ray Observatory has provided stunning evidence for this, showing that colliding galaxies are far more likely to harbor these violently active, X-ray bright black holes than their isolated, peaceful cousins. This is the moment the monster truly awakens, and its roar echoes across the cosmos. The energy released is not just light. The frenetic activity around the black hole can launch twin jets of charged particles, spewing out across thousands of light years at nearly the speed of light. These jets carry a message of regulation, a process astronomers call AGN feedback. The outpouring of energy heats the vast reservoirs of gas throughout the galaxy, stirring it up and preventing it from cooling down and collapsing to form new stars. It is a cosmic balancing act. The collision that initially sparked a firestorm of star formation now, through the awakened black hole, begins to quench it. This creates a self-regulating cycle where the monster, fed by the chaos, in turn governs the future of its entire galactic home. The consequences of this awakening ripple through the newborn galaxy, influencing its ultimate shape, size, and stellar population for the rest of its existence. This final transformation reveals the lasting legacy of the collision. Two elegant spiral galaxies with their spinning disks and vibrant star-forming regions are utterly remade. The violent gravitational tides during the merger act like a cosmic blender, thoroughly randomizing the once orderly orbits of billions of stars. The delicate, rotating disk is shattered, its structure lost as the entire system puffs up into a vast, three-dimensional ellipsoid, a shape resembling a colossal football. This new galaxy is no longer a place of vibrant creation. The immense starburst and the ferocious energy from the awakened black hole have either consumed or violently expelled the galaxy's remaining gas, its primary fuel for new stars. What remains is a population of aging red stars, a galaxy that astronomers often call red and dead. It is a quiet, settled realm, a retirement home for stars, destined to slowly dim over billions of years. Supercomputer simulations, like those from the Illustris TNG project, have beautifully recreated this entire process. They show how the merger of two spiral galaxies naturally and inevitably produces an elliptical galaxy with all the properties we observe in the real universe, from its stellar makeup to its internal dynamics. This is more than a simple change in appearance. It represents a fundamental shift in a galaxy's life cycle, a journey from a dynamic, star-forming youth to a calm, elderly state. This metamorphosis from spiral to elliptical is the final, lasting signature the collision carves into the fabric of a galaxy. Yet, within this grand drama between colossal galaxies, what becomes of the smaller, satellite systems that are merely bystanders to the chaos? While the grand mergers of galactic giants reshape the cosmos, a far more common and subtle drama unfolds in the shadows. This is the story of galactic cannibalism, where the largest galaxies grow by consuming the smallest. In this hierarchical model of the universe, a massive spiral like our Milky Way does not simply exist in isolation. It is the product of a long history of absorbing countless smaller satellite galaxies, a process as relentless as it is destructive. Unlike the spectacular collision of two equal spirals, these minor mergers are a one-sided affair. A tiny dwarf galaxy, drawn in by the immense gravity of its host, is slowly torn apart. The key agent of its destruction is the same tidal force that creates the beautiful arcs in major collisions, but here the effect is far more brutal. The difference in gravitational pull from one side of the dwarf to the other stretches it into long, faint rivers of stars, a process known as tidal disruption. We have a front-row seat to this cosmic feast happening right now in our own celestial backyard. The Sagittarius dwarf spheroidal galaxy is currently in the process of being dismantled by the Milky Way. Over billions of years, our galaxy's gravity has been pulling stars from this satellite, weaving them into a vast, faint stream that completely encircles us. This stream is a cosmic fossil, a ghostly ribbon of light that tells the story of an ongoing accretion event. The physics driving this slow-motion demolition is fascinating. As the small galaxy orbits, it plows through the halo of dark matter surrounding the larger one. This motion creates a gravitational wake, a sort of cosmic drag that saps its orbital energy. This effect, called dynamical friction, acts as a brake, causing the satellite to slowly spiral inward. With each passing orbit, it ventures closer to the galactic core, where the tidal forces grow ever stronger until the dwarf galaxy is completely shredded. Its stars are stripped away and scattered, becoming a permanent part of the Milky Way's extended stellar halo. These quiet events are less visually dramatic than a major merger, but they are absolutely crucial. They are the primary way large galaxies build up their outer halos and grow in mass. This process is a key prediction of our leading model of the universe, cold dark matter, which tells us that structures form from the bottom up, with small things merging to form bigger things. The evidence of these past encounters is written in the stars themselves. By mapping the motions and compositions of stars in the Milky Way's halo, astronomers can identify groups that originated in the same dwarf galaxy, long after it was consumed. These tidal remnants are more than just scars. They serve as a unique astronomical tool, allowing scientists to probe the shape and strength of our galaxy's gravitational field, effectively weighing the invisible dark matter halo that governs everything. This continuous process of assembly and destruction reminds us that even our seemingly stable home galaxy is a dynamic entity, still growing and evolving by absorbing its smaller neighbors. The stars themselves are cosmic historians, each one a living record of the events that shaped our galaxy. This is the field of galactic archaeology, where astronomers do not dig in the dirt but peer into the data of starlight to uncover a past written in motion and metal. Every star carries a unique chemical fingerprint, a signature imprinted at its birth by the composition of the gas cloud from which it formed. Stars born together in the same stellar nursery share this fingerprint and move through the galaxy on similar paths, like a family with a shared history and destination. When two galaxies merge, these distinct stellar families are thrown together into a single, chaotic system. They become mixed, but their fundamental identities remain. Their unique motions and chemical abundances are the artifacts that allow scientists to distinguish native stars from immigrant populations, telling a story of ancient collisions long after the event itself has faded from view. Massive surveys are the tools of this new archaeology. The European Space Agency's Gaia mission has provided a revolutionary census, mapping the precise positions, distances, and velocities of over 1 billion stars within the Milky Way. This vast and moving picture reveals our galaxy not as a serene, finished structure, but as a dynamic archaeological site. Within the data, astronomers have identified distinct streams and clusters of stars moving against the galactic flow, each one the ghostly remnant of a smaller galaxy that was consumed. One of the most striking discoveries is a structure nicknamed the Gaia sausage, or Gaia Enceladus. This is the fossil of a massive dwarf galaxy that plunged into the young Milky Way approximately 10 billion years ago. The violent merger likely sent shockwaves through our galaxy, dramatically thickening its disk and fundamentally altering its architecture. The chemical analysis of these stellar immigrants provides an even deeper timeline. By measuring the ratios of certain elements in a star's atmosphere, particularly the balance between iron and what are known as alpha elements, astronomers can read its history like a tree ring. These elemental ratios act as a clock, revealing the star formation history of the merged galaxy before it was ever consumed. A galaxy that formed its stars in a rapid, intense burst will have a different chemical signature than one that formed stars slowly over a longer period. This forensic approach turns the entire galaxy into a layered history book. Every star is a page recounting a chapter of a violent and dynamic past, from quiet beginnings to colossal impacts. Unlocking these individual stellar stories provides the ultimate test for our grand models of cosmic evolution. The simulations run on supercomputers make specific predictions about how mergers should stir up a galaxy and mix its stellar populations. By comparing those predictions to the actual fossil record we see in stars like those from Gaia Enceladus, we can verify or refine our understanding of the universe's fundamental laws. This historical perspective, reading the past directly from the stars around us, makes the grand saga of galactic collisions feel immediate and personal. It shows that our own Milky Way is a product of this ancient chaos, a thought that inevitably turns our gaze outward to the future of our own local cosmic neighborhood. Our own galaxy is on a direct collision course with its greatest neighbor. The Milky Way and the Andromeda galaxy are racing toward one another at 110 kilometers every second, a trajectory set in motion by their mutual gravitational pull. In roughly 4.5 billion years, this cosmic dance will culminate in a merger, a slow-motion event that will completely reshape our local universe. This will not be a single, catastrophic crash. Instead, the two spirals will first sweep past each other in a breathtaking near miss, their gravitational forces twisting and distorting their iconic structures. They will then swing back for a second, closer encounter before finally coalescing into a single, colossal elliptical galaxy that astronomers have nicknamed Andromeda. Supercomputer simulations like those from the Gadget project have mapped out this entire billion-year sequence. They reveal a startling future for our own solar system. While the Sun will almost certainly be thrown into a much wider, more chaotic orbit within the new hybrid galaxy, the odds of our star or our planets colliding with another star from Andromeda are almost zero. The emptiness of space is our ultimate protection, yet from the perspective of any future Earth, the night sky would become an alien and spectacular canvas. The familiar band of the Milky Way would be gone, replaced by a chaotic swirl of light, the shredded remnants of both galaxies' spiral arms. Brilliant blue starburst regions would ignite as clouds of gas slam together, lighting up the heavens with the birth of countless new suns. This is not a speculative possibility, but a scientific certainty, a future written by the same gravitational laws that govern the fall of an apple. It is a humbling reminder that the cosmos is not a static painting but a living, evolving entity, where even the grandest structures are temporary. This inevitable fate for our galaxy prompts a deeper question about the ultimate destiny of all cosmic architecture in an ever-expanding universe. Beyond the titanic pull of gravity and the ghostly influence of dark matter, another invisible force weaves its way through the chaos. Galactic collisions churn a vast cosmic web of magnetic fields, threads of energy woven through the very fabric of interstellar space. These fields are not passive bystanders. As two galaxies intermingle, the resulting turbulence acts like a cosmic loom, stretching, twisting, and folding these magnetic lines. This violent motion amplifies their strength exponentially, a process akin to the dynamo that creates Earth's magnetic field, but operating on an almost unimaginably larger scale. The outcome is a magnetic tapestry of immense power, an unseen architecture that begins to govern the behavior of the entire system. We can witness this phenomenon in action by observing the brilliant synchrotron radiation pouring from famous mergers like the antennae galaxies. Radio telescopes such as the Very Large Array detect this specific type of light, a clear signature of electrons spiraling at nearly the speed of light along these intensified magnetic pathways. This energy is not merely decorative, it exerts a tangible pressure, pushing back against the inward crush of gravity and influencing how and where giant gas clouds collapse to form new stars. These magnetic fields also act as cosmic highways, channeling incredibly energetic particles accelerated in the merger's shock waves. Furthermore, they play a subtle but vital role in the galactic core, helping to transport angular momentum away from the central regions. This process effectively removes the spin that would otherwise keep gas in a stable orbit, allowing more material to flow inward and feed the awakening supermassive black hole, fueling the brilliant quasar at the heart of the merger. This intricate interplay of forces reveals a fundamental truth about our universe. To truly understand a galactic collision, we cannot rely on gravity alone. We must listen to the messages carried by light, by motion, and by these invisible magnetic threads, a multi-messenger approach that captures the full, chaotic symphony of cosmic evolution. The interstellar gas is the true lifeblood of a galaxy, and in a collision, it undergoes a brutal thermodynamic transformation. While the stars glide past each other in the vast emptiness, the gaseous disks of the two galaxies have no such luxury. They slam into one another at supersonic speeds, creating colossal shock waves that ripple through the interstellar medium. Think of it as a sonic boom, but one generated on a scale so immense it dwarfs entire star systems. These galactic-scale shock fronts are the engines of violent change, traveling through the gas and heating it to staggering temperatures of millions of degrees. This process, known as shock heating, is a brutally efficient conversion of raw kinetic energy into pure thermal energy. The chaotic motion of the entire collision is transformed into an invisible, seething heat that permeates the gas, fundamentally altering its state. This is where the invisible violence of the merger becomes detectable. This multi-million-degree plasma glows intensely in X-rays, and space observatories like Chandra have given us our eyes to see it. Their observations of famous mergers reveal vast, luminous halos of this superheated gas, mapping the invisible fury of the collision and providing a direct measure of its immense energy budget. The fate of this gas becomes a central drama. In the outer regions of the merging system, this intense heat acts as a powerful brake on star formation. The gas is so hot and energetic that the pressure prevents it from cooling down, collapsing, and condensing into the dense clouds required to birth new stars. It is effectively quenched, trapped in a diffuse, hot state. Yet, the same forces that heat this gas also trigger a paradoxical flow. The immense pressure of the shock waves can slam cooler, denser gas inward, funneling it directly toward the galactic core. This delivered fuel is what ignites the brilliant central starbursts, creating a firestorm of new stars at the very heart of the chaos. The behavior of this gaseous component, whether it is heated into oblivion, compressed into new suns, or eventually expelled entirely, is what ultimately writes the final chapter for the newly forged galaxy, determining if it will be a vibrant stellar factory or a quiet, red and dead realm. A faint cosmic fog hangs in the deepest voids between galaxies. This is diffuse light, one of the most ghostly and beautiful monuments left behind by ancient collisions. It is the glow of countless orphaned stars cast adrift from their galactic homes to wander the immense darkness. This stellar haze manifests in two primary forms. Within the crowded metropolises of galaxy clusters, you find intracluster light, a collective glow built from stars stripped from many different galaxies over billions of years. Then there are the more specific relics of a single merger, the vast, faint streams and shells of tidal debris that wrap around the remnant galaxy like the tattered ribbons of a burst balloon. The physics that creates these phantoms is purely gravitational. During the chaotic close encounters of a merger, stars can be whipped around by the shifting gravitational fields and flung outward with such energy that they completely escape the pull of their host galaxy. They become permanent exiles, either wandering alone in the intergalactic void or contributing to a shared pool of light that fills the space between galaxies. The Hubble Space Telescope has peered into the heart of massive clusters like the Coma Cluster and detected this very glow. The sheer amount of light is staggering, accounting for a significant fraction of the total stellar mass in the cluster. This faint illumination is not a minor detail. It is a direct fossil record, a paleontological dig site written in starlight that reveals a long history of violent interactions. Each of these orphaned stars is a silent witness to a past cataclysm. Their existence sparks profound questions. Could planets orbit these intergalactic stars? And if so, what would life be like in such profound isolation? On a world with a night sky devoid of any galactic structure, only an endless star-speckled black. This diffuse component is a permanent signature of the universe's relentless cycle of destruction and creation. The very presence of these stellar ghosts, no longer bound to any single galaxy, challenges our most fundamental definitions of what a galaxy even is. Our own solar system, a tiny island of life in a vast ocean of stars, faces a future galactic merger with remarkable resilience. The sheer emptiness of space is its greatest shield. With stars typically separated by trillions of miles, the chance of our Sun physically colliding with another star during the Milky Way's merger with Andromeda is almost zero. The real danger is not a direct impact but a gravitational whisper. A star passing even a full light year away could act like a subtle hand, gently nudging the countless icy comets in our solar system's distant Oort cloud. This gravitational perturbation could send a shower of these icy bodies on a new trajectory, some falling inward toward the planets. Such a comet shower could pose a challenge for any life, potentially leading to a period of increased impact. Yet, sophisticated computer models of our future galactic collision offer reassuring odds. The probability of another star passing close enough to our solar system to cause such significant disruption is calculated to be less than 1%. A more diffuse threat may come from the brilliant, short-lived stars born in the merger's starburst. When these massive stars die in supernova explosions, their intense radiation could, from a relatively nearby location, potentially affect the atmospheres of planets like Earth. Even with this increased activity, the vast distances involved offer substantial protection. This reveals a profound truth about our cosmic address. Planetary systems are incredibly stable structures, their long-term fates shaped far more by the aging of their own star than by the grand-scale chaos of a galactic collision. This stability offers a comforting perspective for the possibility of life elsewhere in the universe, suggesting that countless worlds may safely witness the most spectacular celestial events from a secure distance. This cosmic shelter for individual planets makes the final, large-scale transformation of the galaxy itself all the more significant. The grand dance of galaxies unfolds against an even vaster cosmic backdrop, a universe that is not just expanding but accelerating in its flight. This cosmic acceleration is driven by the most enigmatic force in physics, dark energy. Think of it as a fundamental pressure woven into the fabric of space itself, a force that acts in direct opposition to gravity's relentless pull. On the grandest scales, dark energy dominates, pushing galaxies apart and causing the cosmos to become increasingly vast and empty as time flows onward. This overarching expansion sets a profound context for the chaotic mergers we have explored. In the dense, crowded universe of the distant past, galactic collisions were a frequent and dominant process, the primary engine of cosmic construction. But as dark energy stretches the cosmic tapestry, it dilutes the population of galaxies, making these spectacular encounters far more rare in the future. We are living in a special cosmic era, a window of time where the local pull of gravity can still overcome this global expansion, allowing titans like the Milky Way and Andromeda to remain bound and destined for their colossal merger. The fate of any two galaxies hinges on this delicate balance. If their mutual gravitational attraction is strong enough, they can resist the cosmic tide and eventually collide. If not, the stretching of space will inevitably pull them apart, dooming them to eternal separation. This introduces a poignant timing to our view of the heavens. For any future civilization that might arise in the merged Andromeda galaxy, the night sky would tell a far lonelier story. Over trillions of years, the accelerating expansion driven by dark energy would push every other galaxy beyond the visible horizon. Their universe would be an island in an endless dark void, the brilliant evidence of cosmic evolution and collision having faded completely from view. The physics of this mysterious energy thus writes the final act for the drama of galactic collisions, framing our dynamic present as a transient, vibrant chapter in the life of the cosmos. It highlights the ephemeral nature of the celestial structures we take for granted, reminding us that we are witnesses to a spectacle that has a definite beginning, middle, and end. Our own brief lives seem to place these billion-year events forever out of reach, yet astronomers possess a remarkable tool for bending time itself, a concept known as cosmological look-back time. Because light takes time to travel across the vastness of space, when we peer at a distant galaxy, we are not seeing it as it is today, but as it was when its light began the long journey to our telescopes. The farther out we look, the further back in time we see. This transforms the entire cosmos into a living history book. The Hubble Space Telescope's iconic deep-field images provide the ultimate proof. They reveal a universe teeming with young, tangled galaxies, many caught in the act of colliding. By counting these interacting systems at different distances, and therefore different cosmic eras, scientists can construct a statistical movie of the universe's evolution, showing how the frantic merger rate of the early cosmos gradually slowed to the more measured pace we see in our local neighborhood today. This is how we watch a single collision unfold, not by waiting, but by looking out at a gallery of snapshots, each one capturing a different stage of the process. But light alone is not enough. To see the full picture, we must observe the cosmos across the entire spectrum of light, with each wavelength revealing a different chapter of the story. Our eyes see only the optical light, the glow of stars. To peer through the veils of dust thrown up by a collision, we need the infrared eyes of the James Webb Space Telescope, which can detect the heat from hidden starbursts blazing inside dense clouds. Radio telescopes trace the faint emission from vast reservoirs of cold hydrogen gas, the raw fuel for future stars, and observatories like Chandra capture the searing X-ray glow of multimillion-degree plasma, the shock-heated gas that tells of the collision's most violent moments. By weaving all these different views together, we get a holistic, multi-sensory understanding of an event that would otherwise remain invisible in its entirety. These observations provide the raw data, the still frames of our cosmic movie. To animate them, we turn to the digital universes created by supercomputers. These are not mere animations, they are complex physical models that simulate the laws of gravity, hydrodynamics, and radiation across billions of virtual particles. Physicists can set up initial conditions mimicking two spiral galaxies, press play, and watch as the simulation calculates their gravitational dance, their gas collisions, and their resulting starbursts over billions of years of compressed time. The true power lies in the comparison. When the outcome of a simulation closely matches what we actually see in a real galaxy merger, it gives us tremendous confidence that our understanding of the underlying physics is correct. It allows us to run experiments we could never perform in reality, testing how different variables change the outcome. This powerful synergy between observation and simulation compresses eons into a narrative we can grasp, transforming us from passive stargazers into active interpreters of the grandest story there is. With every new telescope and every more powerful simulation, we refine this story, promising to reveal even deeper layers of this cosmic choreography in the years to come. The very first galaxies were not the grand spirals we see today. They were tiny, fragile things, the cosmic equivalent of village settlements that would one day merge into vast metropolitan cities. In the universe's first few 100 million years, these small building blocks of stars and gas began to draw together, initiating the very first acts of galactic construction. This was the dawn of hierarchical growth, the foundational process where small structures merge to form ever larger ones. The James Webb Space Telescope is our time machine to this distant era, and its observations are revolutionizing our understanding. It reveals that these primordial mergers were not rare events, they were the rule. Galaxy collisions were rampant in the young, dense cosmos, and they may have been absolutely essential for solving one of astronomy's great mysteries, the rapid appearance of supermassive black holes. In today's universe, these giants take billions of years to grow, but in the early cosmos they appeared astonishingly fast. The physics of these ancient collisions points to an answer. When two of these early galaxies merged, the resulting chaos could have directly collapsed massive clouds of pristine gas into black hole seeds of unprecedented size, giving them a colossal head start. These early mergers were also cosmic crucibles for rapid growth, violently funneling gas inward and building up the mass of the first true galaxies at a breakneck pace. The environment itself was fundamentally different. The gas involved was pure, uncontaminated by the heavy elements that later generations of stars would forge. This purity changed everything about how it behaved. Without metals to help it cool efficiently, this primordial gas may have resisted collapse, only giving way to form stars under the immense pressures generated by a violent merger. The first stars born from these collisions were likely behemoths, hundreds of times more massive than our Sun, burning ferociously and dying young. The collective energy from these stellar giants and the first quasars then performed a cosmic service of immeasurable importance, reionizing the universe. Their intense ultraviolet radiation blasted through space, breaking apart the neutral hydrogen atoms that filled the cosmos and rendering the universe transparent to light for the very first time. Studying these ancient events is like watching the infancy of galactic evolution, a time when the basic rules were being written in fire and gravity. Every massive galaxy we see today, including our own Milky Way, contains the fossilized imprint of this violent, formative era, a foundational chapter written by the first collisions. Scattered throughout the cosmos are ghostly giants, cosmic phantoms that defy our expectations of what a galaxy should be. These are the ultra-diffuse galaxies, vast islands of stars as large as our entire Milky Way, yet so faint they are nearly invisible. They contain just a tiny fraction of the stars we would expect, making them some of the most enigmatic objects in the universe. How could something so large hold so little light? The answer may lie in the chaos of collisions. One compelling theory suggests these galaxies are the puffed-up remnants of violent encounters. During a merger, a small dwarf galaxy can be caught in a gravitational tug of war. The powerful tidal forces stretch it, not by ripping it apart completely, but by pulling its stars into a much wider, more diffuse orbit. The galaxy's structure is dramatically inflated, transforming it from a compact sphere into a vast, faint haze, its stars scattered across an immense volume of space like a handful of dust thrown into the wind. This process strips away its gas, the fuel for new stars, leaving behind an aging, quiet population. Yet there is another possibility. Some of these ghosts might be failed galaxies, systems that lost their potential for stardust early in their lives. As they plunge through the dense, hot gas within a massive galaxy cluster, they can experience a phenomenon called ram pressure stripping. Imagine a galaxy sailing through this intergalactic medium like a swift boat through water. The intense pressure of the encounter can blow away its delicate gas reserves, robbing it of the material needed to form new generations of stars. It is a cosmic quenching, leaving the galaxy permanently stunted and faint. The mystery deepens when we look at clusters like Coma. Here, astronomers found that many ultra-diffuse galaxies possess a surprising abundance of ancient, dense star clusters known as globular clusters. This is a crucial clue. A small, fragile galaxy should not host such a rich collection of these massive clusters. Their presence strongly suggests these ghosts are not born faint, but are the stripped-down skeletons of galaxies that were once far more massive and proud, their outer layers of stars torn away by repeated gravitational encounters, leaving only their dense core systems behind. This discovery challenges the simplest models of how galaxies form and evolve. It reveals that the outcomes of gravitational interactions are far more diverse and subtle than we once imagined. Is a given ultra-diffuse galaxy a puffed-up dwarf, a failed giant, or the skeletal core of a once larger system? Unraveling the specific history of each ghost is an active frontier in astronomy, a puzzle that forces us to look more carefully at the quieter, more delicate signatures that collisions leave behind across the cosmos. A galaxy's graceful spin is one of its most defining features, a beautiful expression of order in the cosmos. This rotation is governed by a fundamental physical property known as angular momentum, a kind of cosmic inertia that keeps a spinning disk stable and intact. In the quiet solitude of deep space, this momentum is conserved, a constant that maintains the galaxy's elegant form across billions of years. But this order is an illusion of isolation, one that shatters the moment another galaxy draws near. The gravitational embrace of a collision introduces a powerful and chaotic force called torque. This is not a gentle nudge. It is a violent twisting force, a gravitational lever that reaches into the very heart of the galaxy and rewrites its rules of motion. During a close encounter, these gravitational torques act like invisible hands, grabbing hold of stars and gas and violently transferring their angular momentum. Some of this foundational spin is siphoned away from the visible galaxy entirely, handed off to the immense, unseen halo of dark matter that surrounds it. In a major merger between two grand spirals, the effect is catastrophic. The two beautifully ordered disks of stars, each with its own distinct sense of spin, are thrown into a chaotic gravitational blender. Their collective angular momentum is not lost, but it is utterly redistributed, scrambled into a random, three-dimensional froth of stellar motions. The final product of this cosmic churning is a slowly rotating, or even non-rotating, elliptical galaxy, a system where stars no longer flow in a coherent disk but buzz around the center on random, chaotic orbits like a swarm of immense bees. This is the fundamental metamorphosis from a spiral to an elliptical, the loss of a galaxy's soul, its ordered spin. The effects of these encounters are not always so total. In a minor merger where a small satellite galaxy is consumed by a larger spiral, the disruption is more subtle but no less telling. The gravitational perturbation from the incoming dwarf can warp the larger galaxy's disk, bending it like a vinyl record left in the sun, or thicken it, puffing it up with a haze of disturbed stars. Evidence suggests our own Milky Way experienced exactly this. The ancient Gaia-Enceladus merger, which occurred billions of years ago, likely sent powerful waves through our galactic disk, thickening it and leaving a permanent imprint on the motions of stars we can still measure today. The physics driving this transformation is a complex ballet of gravitational interactions, where every single star exerts a tiny pull on every other. The net result is a vast and irreversible exchange of energy and momentum, a process that supercomputer n-body simulations visualize with breathtaking clarity. These digital experiments show the graceful spiral arms dissolving, their ordered rotation unraveling into the random motions that define the new elliptical galaxy. For astronomers, this change in rotation is a key diagnostic tool, a fingerprint of a past collision. By using spectrographs to measure the velocities of stars across a galaxy, they can create a map of its rotational support. A galaxy where stars on one side are moving toward us while stars on the other side are moving away reveals a clear, ordered spin. A galaxy where the stellar velocities show no such clean pattern, where motion is random in every direction, is almost certainly a merger remnant, a silent witness to an ancient chaos. The cessation of a galaxy's spin marks the end of its life as a vibrant, star-forming spiral, and its rebirth into a calmer, more sedate existence. This profound change in a galaxy's fundamental dynamical state is one of the most direct and dramatic consequences of the hidden physics that governs gravitational encounters, a permanent alteration written into the motions of billions of suns. Hidden within the final moments of a galactic merger is a signal that will soon let us listen to the cosmos itself. When two supermassive black holes, each with the mass of millions or even billions of suns, spiral together at the heart of a newly merged galaxy, they do not collide quietly. Their immense orbital motion sends powerful ripples through the very fabric of spacetime. These are gravitational waves, but they are nothing like the high-frequency chirps detected from stellar mass black holes by observatories like LIGO. The waves from these supermassive binaries are vast and slow, with wavelengths that can span entire light years and frequencies far too low for any ground-based instrument to hear. They represent a cosmic bass note, a deep hum that has until now been completely silent to us. To tune into this new channel of the universe, we must go to space. The Future Laser Interferometer Space Antenna, or LISA, is a mission designed to do exactly that. It will consist of 3 spacecraft flying in a giant triangular formation, millions of kilometers apart, using lasers to measure the infinitesimal stretching and squeezing of space as these low-frequency waves pass by. The signal it will detect is not a brief blip. It is a long, evolving song that can last for months or even years as the black holes slowly inspiral. This complex chirp will encode a wealth of information within its waveform, allowing scientists to directly read the masses and spins of the black holes and even probe the properties of the dense, chaotic environment surrounding them. This data is crucial because the final merger of these titans is not a foregone conclusion. Theory suggests that after a galactic collision, the 2 supermassive black holes can sink to the center and become locked in a stable binary, orbiting each other for billions of years without ever getting closer. Their immense gravitational attraction is counteracted by their own angular momentum, a cosmic stalemate. To finally coalesce, they need a mechanism to shed that momentum. This might be provided by a third black hole intruding on the system, a gravitational nudge that breaks the deadlock, or by a massive, swirling disk of gas that acts as a brake, allowing the black holes to spiral the final distance. By detecting the gravitational waves from thousands of such systems, LISA will conduct a full census of supermassive black hole binaries across the universe, revealing exactly how they overcome this final hurdle to merge. This will be the ultimate direct confirmation of the entire galactic merger paradigm. For the first time, we will not just see the aftermath of these colossal events, we will hear the final, resonant note of the collision itself, a new sense with which to perceive the hidden physics shaping our universe. This brilliant starburst, for all its creative power, carries the seeds of its own destruction. The very same supernova explosions that light up the merging galaxies begin to drive powerful galactic winds, vast outflows of superheated gas that rush outward at millions of miles per hour. These winds act like a cosmic hurricane, scouring the galaxy of its remaining star-forming fuel and blowing it far out into the surrounding circumgalactic medium. This is a crucial act of self-regulation. The galaxy, in a single violent burst of creation, forges the heavy elements that enrich the cosmos and then uses the explosive energy of that process to expel the very material that birthed it. This supernova feedback is one of the universe's primary mechanisms for quenching star formation, ensuring that a galaxy cannot simply burn through all its fuel in one frantic, unsustainable firestorm. Simultaneously, the monster at the center awakens to its own regulatory role. The active galactic nucleus, or quasar, does more than just shine. It injects a staggering amount of energy back into its surroundings. Through immense jets and radiation pressure, this AGN feedback heats the galaxy's halo of gas, keeping it so hot and diffuse that it cannot cool down, collapse, and flow back in to form a new generation of stars. Think of it as a cosmic thermostat, preventing the galaxy from overheating with too much stellar activity. Without these balancing feedback mechanisms, our models of the universe simply fail. Cosmological simulations show that if gravity acted alone, without the disruptive counter forces of supernova winds and quasar activity, galaxies would grow impossibly large and bright, forming far more stars than we ever observe in the real cosmos. It is this delicate interplay between construction and destruction, between gravity's pull and feedback's push, that creates the galaxies we see. This feedback cycle transforms a galaxy from a passive collection of stars into a dynamic, self-regulating ecosystem. It forges a balance that dictates not only a galaxy's final mass and shape, but the entire story written in its starlight, a story of brilliant, self-limiting fire. Among the most enduring relics of a galactic collision are the dense, glittering balls of stars known as globular clusters. These ancient structures, each containing hundreds of thousands to millions of stars in a tight sphere, are like cosmic time capsules forged in the fires of immense pressure. During the violent merger of two galaxies, shock waves slam into giant clouds of molecular gas, compressing them with a force far beyond what occurs in a quiet galaxy. This extreme compression triggers a uniquely intense burst of star formation, creating not individual stars but entire, massive clusters all at once. We see this prolific factory at work in nearby mergers like the Antennae galaxies, where astronomers have identified dozens of brilliant, young globular cluster candidates blazing within the chaotic interaction zone. These newborn clusters are spectacularly dense, with stars packed so closely that the night sky from a hypothetical planet within one would be a perpetual star-drenched twilight. What makes them so special is their incredible resilience. While the delicate tidal tails and distorted spiral arms of a merger will eventually fade and disperse over billions of years, these globular clusters possess enough gravitational glue to hold themselves together, surviving virtually unchanged for the entire age of the universe. They become permanent fossils of the violent event that created them, Our own Milky Way's halo is studded with these ancient stellar spheres, and their origins tell a fascinating story of cosmic adoption. Many of these clusters did not form within the Milky Way itself. Instead, they were likely born within smaller dwarf galaxies that our galaxy later consumed. When those satellite galaxies were torn apart by tidal forces, their hardy globular clusters were stripped away and adopted into the Milky Way's halo, where they continue to orbit as celestial orphans. By studying the ages and chemical compositions of these clusters, galactic archaeologists can read a separate, independent history of our galaxy's growth. Each cluster's unique fingerprint of elements reveals the conditions of its birth environment, allowing scientists to piece together which clusters are native and which are immigrants from long-vanished galactic companions. These dense stellar systems thus preserve a pristine record of the violent, formative epochs that built galaxies like our own, their silent, enduring orbits echoing the chaos of their creation. The very atoms that make up our world carry a hidden history of cosmic violence. A galaxy's chemical makeup, what astronomers call its metallicity, is more than just a list of elements. It is a living diary, a detailed record of every star that has ever lived and died within it. In the quiet solitude of a mature galaxy, this diary is written slowly, one page at a time. But a galactic collision rips through that book and rewrites entire chapters in a blaze of creative fury. These violent encounters trigger starbursts of such intensity that they fundamentally alter the galaxy's chemical identity, enriching its cosmic brew with a sudden infusion of newly forged elements. The most massive stars born in these firestorms are the universe's great alchemists. They burn through their nuclear fuel in just a few million years, a cosmic blink of an eye, and end their lives in cataclysmic supernova explosions. In their final moments, these stellar furnaces fuse lighter elements into heavier ones, blasting out newly created oxygen, silicon, and iron across light years of space. This sudden, rich harvest of metals seeds the surrounding gas clouds, dramatically increasing the overall metallicity of the galactic environment. This enriched material then becomes the building blocks for everything that follows. The next generation of stars that forms from this polluted gas will be born richer in these heavy elements from the very beginning. Their planetary systems, should they form, will have a greater abundance of the raw materials like iron and silicon that are essential for building rocky worlds. Yet this process is not contained. The same ferocious supernova explosions that create these elements also drive powerful galactic winds, which can sweep this newly enriched gas right out of the galaxy entirely. This is a form of cosmic pollution on an unimaginable scale, as heavy elements are expelled into the vast intergalactic medium, forever altering the chemical potential of the void itself. We can see the lasting signature of this violent chemical enrichment in the galaxies around us. Observations of massive elliptical galaxies, the known products of ancient mergers, often show a distinct chemical gradient. Their central regions, where the starburst was most intense, glow with the light of stars that are significantly richer in metals than those in the galaxy's outer halo. This is the fossilized imprint of that central firestorm, a permanent chemical monument to the collision that created it. This rapid chemical maturation helps solve a key puzzle of cosmic evolution. The first galaxies in the early universe were composed almost entirely of the primordial elements hydrogen and helium. They were metal-poor. How did they evolve into the chemically rich systems we see today? Systems capable of forming planets like Earth. Galactic collisions provided a crucial catalyst, a mechanism to accelerate this chemical enrichment dramatically and seed the cosmos with the elements necessary for complexity and ultimately for life. The specific pattern of elements we see in a star today, can therefore tell us if it was born from gas that was stirred and enriched by an ancient, violent merger, a chemical fingerprint of chaos written in starlight. This cosmic complexity, with its countless gravitational tugs and turbulent gas, creates a puzzle far too intricate for simple mathematics. To truly comprehend the hidden physics of galactic collisions, we must build our own digital universes. This is the realm of computational astrophysics, where scientists use some of the world's most powerful supercomputers to model the dance of galaxies. A single simulation must account for the gravity of billions of dark matter particles, the fluid dynamics of interstellar gas, the ignition of new stars, and the explosive feedback that regulates it all. It is a calculation of almost unimaginable scale. To make this possible, researchers create virtual worlds inside the machine. Pioneering projects like ILLUSTRIS-TNG, EAGLE, and FIRE start with the initial conditions of the early universe and then press play, applying the known laws of physics to watch as their digital cosmos evolves over billions of years. The ultimate test is whether the galaxies that emerge from these virtual runs look and behave like the real ones we observe through our telescopes. Do they have the right range of masses, the correct distribution of shapes, and a believable history of collisions? The answer is not always yes, and that is where the real discovery begins. Because the universe is too vast to model in perfect detail, these simulations rely on intelligent approximations. For processes that occur on scales too small to resolve directly, like the formation of a single star within a giant cloud, scientists develop what are known as subgrid models. These are simplified yet physically grounded recipes that represent the overall effect of these small-scale events on the larger galactic environment. The choice of these recipes is crucial. A different model for how supernovae inject energy into the gas can determine whether a simulated galaxy remains a vibrant spiral or transforms into a red and dead elliptical. This makes the constant validation against real-world observations absolutely essential. Every stunning visualization from these simulations is more than a beautiful animation. It is a precise, quantitative prediction. By comparing these digital outcomes with the data from observatories, astronomers can run experiments, testing which physical models most accurately recreate the universe we see. They can, for instance, turn off the feedback from supermassive black holes in a simulation and watch as galaxies grow impossibly bright and massive, proving just how critical that regulating force truly is. The grand challenge is a constant push for higher resolution and greater physical fidelity, all while keeping the computations feasible. This field advances hand in hand with computer technology, each new generation of processors allowing for a sharper, more detailed view into the cosmic dance. These digital laboratories have become indispensable, giving us a unique power to rewind and fast-forward through time, to isolate single variables, and to run controlled experiments on the universe itself, uncovering the hidden rules written in gravity and light. The hunt for these cosmic duos confirms a key prediction of the merger model. When two galaxies collide and combine, their central supermassive black holes are also destined to meet. Dragged by friction and gravity, these colossal objects sink toward the heart of the new galaxy, eventually forming a binary system, a pair of monsters locked in a gravitational dance. Observing these dual-active galactic nuclei is incredibly difficult. Their orbital separation can be minuscule on a cosmic scale, sometimes smaller than our solar system, and far below the resolution limit of most telescopes. Yet, astronomers have confirmed their existence in a handful of systems. They use ingenious techniques like spectroscopy, which can detect the subtle, conflicting Doppler shifts in light from two separate disks of superheated gas, each whirling around its own black hole. Even more precise is Very Long Baseline Interferometry, or VLBI, which effectively combines radio telescopes from across the globe to create a virtual instrument the size of Earth, offering a sharp enough view to resolve two distinct, brilliant cores shining within a single, chaotic galaxy. The discovery of each new binary is a triumph, a direct snapshot of the merger process in action. But this dance faces a profound theoretical hurdle known as the final parsec problem. As the two black holes spiral closer, they eventually clear their immediate surroundings of stars and gas through gravitational slingshots. With nothing left to interact with and steal their angular momentum, their inward spiral could stall when they are just a few light-years apart. They might remain locked in this cosmic standoff for a time longer than the current age of the universe, never completing their merger. To solve this, physicists propose that a massive, swirling circumbinary disk of gas may provide the necessary break. The gravitational tug between the black holes and this disk could sap their orbital energy, allowing them to bridge that final, critical gap. This makes the search for these systems a primary goal for observatories. Each confirmed binary is a precursor to the most energetic events in the cosmos, the progenitors of the low-frequency gravitational wave, sources that the future LIS mission is designed to detect. Their existence provides the ultimate link in the chain of cosmic structure formation, proving that the collision of galaxies inevitably leads to the mergers of the titans that reside within them, a fundamental cycle of destruction and creation written into the laws of physics. A galaxy's cosmic address shapes its destiny as profoundly as its own mass. The violent, transformative collisions we often envision are not the only story. The environment a galaxy calls home dictates the rhythm and outcome of every interaction. Picture the difference between a quiet rural village and a bustling metropolitan downtown. In the sparse cosmic countryside known as the field, galaxies drift in relative isolation. Here, when two neighbors feel a mutual gravitational pull, they have the space and time for a slow, intimate dance. Their relative speeds are low, allowing gravity to gently intertwine their structures over billions of years, often culminating in the complete merger that forges an entirely new galaxy. Our own local group, with the Milky Way and Andromeda locked in their gradual approach, is a perfect example of this slower, more transformative process. Now travel to the heart of a massive galaxy cluster, a dense metropolis of thousands of galaxies. The environment here is one of controlled chaos. Galaxies whip past one another at staggering speeds, thousands of kilometers every second. At these velocities, two galaxies cannot slow down enough to form a lasting gravitational bond and merge. Instead, they experience high-speed flybys, a process astronomers call harassment. These are not slow, graceful encounters, but rapid, impulsive gravitational shocks. As a galaxy streaks past its neighbor, the intense but brief tidal pull can strip away its outer halo of stars and gas, leaving behind distorted, puffier shapes without ever leading to a full union. It is a series of cosmic drive-by shootings, each one leaving its mark. The cluster environment presents another, more insidious threat, a phenomenon known as ram pressure stripping. Galaxy clusters are filled with a seething, thin soup of superheated gas called the intracluster medium. When a spiral galaxy plunges through this dense plasma, the experience is like sticking your hand out of a car window at high speed. The intense pressure of the encounter acts as a cosmic wind, violently blowing the galaxy's own cool gas reserves out of its disk. This gas is the very lifeblood of star formation. Stripped of this fuel, the galaxy is quenched. Its ability to create new stars is shut down, often long before any collision can trigger a starburst. The galaxy is left to slowly redden and fade, a process that is far less effective in the lonely, low-density field where such intergalactic winds are gentle or non-existent. This fundamental environmental dependence means you cannot understand a galaxy by looking at it in isolation. Its very shape, its stellar population, and its history of star formation are a direct product of its cosmic neighborhood. A massive, red and dead elliptical galaxy in a cluster may have been quenched by its harsh environment, while a similar-looking galaxy in the field might be the product of an ancient, transformative merger. The context of the collision is everything, a crucial layer of complexity that explains the stunning diversity of galaxies we see when we survey the heavens. How then do we begin to read the subtle clues of these past encounters, to distinguish the scars of harassment from the ruins of a full merger? The next generation of observatories will transform our silent movies of galactic collisions into a full sensory experience. The Vera C. Rubin Observatory, with its legacy survey of space and time, will act as the ultimate cosmic surveillance system. Night after night for an entire decade, it will scan the entire southern sky, not just taking a single picture but creating a dynamic film of the heavens. It will track millions of interacting galaxies, watching as tidal tails grow, as starbursts ignite and fade, and as the structures of these colossal systems evolve in real time. This vast data stream will provide the statistical backbone for understanding not just how collisions happen, but how common each type of outcome truly is across the universe. Meanwhile, the James Webb Space Telescope acts as our infrared scalpel, cutting through the veils of dust that have long hidden the inner workings of these chaotic events. It peers directly into the hearts of nearby mergers to witness the ignition of star clusters and the feeding of black holes. More profoundly, it looks back to the dawn of cosmic time, observing the very first galactic building blocks as they began their violent construction mergers, revealing the initial conditions for all that followed. To understand the fuel that powers these cosmic firestorms, we turn to the radio universe. The square-kilometer array will map the distribution of neutral hydrogen gas within and between colliding galaxies with a sensitivity and resolution that is simply unprecedented. This will allow us to trace the invisible rivers of star-forming fuel as they are pulled, compressed, and shock-heated during an encounter, showing us precisely how the chaos dictates the future of stellar birth. And then there is the sound. The Laser Interferometer Space Antenna, or LISA, will open an entirely new sense with which to perceive these events. It will not see the light from the collision, but will hear the low-frequency hum, the space-time vibrations generated as the supermassive black holes at the cores of merged galaxies spiral together. This will be the direct, incontrovertible confirmation of the final act, allowing us to census these cosmic titans and understand the physics that brings them together. These observatories do not work in isolation. Their collective data will fuel the next generation of supercomputer simulations, creating digital universes of such fidelity and detail that they will blur the line between model and reality. We are moving from simply describing what a collision looks like to precisely predicting its every consequence, a shift that promises to unlock the deepest secrets of how gravity, dark matter, and feedback conspire to build the cosmos. The hidden physics that has guided these events for billions of years is about to step into the light. From the ghostly pull of dark matter to the final burst of stellar fire, these collisions are the universe's great sculptors. Gravity's hidden hand, working through tidal forces and shock waves, forges new structures from the ruins of the old. The brilliant starbursts and the awakening of black holes are not endpoints, but transformative events in an endless cycle of creation and destruction. This cosmic drama reshapes vibrant spirals into quiet ellipticals, seeding the void with new stars and enriching the cosmos with the very elements that make our world possible. The evidence for this grand saga surrounds us. It is written in the ghostly tidal streams that wrap around our own Milky Way, and it blazes across the heavens in the tangled forms of merging galaxies captured by our most powerful telescopes. This story points toward an inevitable future, one where our own galaxy will be utterly remade in a final grand merger. As Carl Sagan so beautifully expressed, the cosmos is within us. We are made of star stuff, and that star stuff itself was forged and scattered across the galaxy in these ancient, violent encounters. Let this knowledge forever change your gaze upon the night sky. That serene tapestry of light is not a static painting. It is a living, dynamic, and sometimes violent arena where the very architecture of our cosmic home is continually rewritten. We invite you to share your own reflections and questions in the conversation below, and to join us for our next exploration into the wonders of the universe.